So in this paper, we are discussing about the enhancement of the super resolution algorithm based on the skip residual dense network. So they are proposing SRDN, which is a skip residual dense net. By using this skip residual dense net, they are saying super resolution enhancement is being done. So first they are designing a model, a 2-channel SRDN. This 2-channel SRDN is used to extract the deep feature information. The 2 channels which we are using, they have the same network structure, and these 2 channels are being connected by the skip connections. Now I will show that. This is what they have proposed SRDN. This is channel 1. This is channel 2. They are using 2 channels. This SRDN is capable of extracting the features, and that's why this is called dual channel SRDN. This is proposed in this paper. These 2 channels, you can observe here, these 2 channels are having the same network architecture. There is no difference in the network architecture, and they are connected by the skip connections. When we are connecting output of one layer to the next layer as an input, this type of connections we are calling as skip connections. So we are taking an SRDN network. This SRDN network is proposed by them. This is having 2 channels, and these 2 channels are similar, and these 2 channels are connected by the skip connections. So this model, whatever they are using the model, this model is first dividing the input image into 2 components. The low resolution image, it is dividing into 2 components. For dividing it into 2 components, it is taking the help of the guided filtering. So the 2 components features, whatever the 2 components we get by using this guided filtering, the features of the 2 components is learned by the one convolution layer. And after learning the features, for this convolution layer, we are connecting 3 layers double channel SRDN network. I will show that. You can observe here. This is an input image. This is a low resolution image. By using the guided filtering, we are getting 2 components from the input image, input low resolution image. These 2 components we are giving to the convolution layer. 2 convolution layers are there. So these 2 convolution layers are learning the parameters by using the 2 components. Now we are giving the output of these 2 convolution layers to the 3 SRDN networks. In each SRDN network, we have 2 layers, 2 channels, we can say, channel 1 and channel 2. And these channel 1 and channel 2, as we mentioned already, these 2 channels are similar, and they are connected by the skip connections. Now the extracted features from the channel 1 and channel 2 at the output of the third SRDN, both features are combined by using this concatenation operation. So now we are using concatenation operation to combine the features of the 2 channels. After that, so we are using a upsampling network and one convolutional operation. After the upsampling and convolution, we are getting the super resolution image. Here in this paper, they are using a joint loss function. Joint loss functions means they are using 3 losses: content loss and perceptual loss and color discrimination loss. When we are training the images, at that time, the difference between the original image and the predicted image, whenever we take the difference, we use it to call as an error or loss. Now they are using 3 types of the losses: content loss and perceptual loss and color discrimination loss in order to evaluate. And they are mentioning this algorithm is giving a very good results. Super resolution means we are giving a low resolution input, low resolution image input, and we are getting the high resolution image output. For this type of the problems, We are addressing from the past times, we have been many papers which addressed the super resolution problem. Now in the artificial intelligence, in the field of the artificial intelligence, the more attention is being given for the super resolution problem. And so one example is given here. In the class old movies, they used to compress the image. And after the compressing the image, this is the original image example. Now they are compressing that image. Example, this is a CI compressed image. And they are transmitting these images. Why they are not transmitting the original image means it is the wastage of the data. More amount of data is required for the transmission, and bandwidth, the network bandwidth also becomes more. So they will transmit this compressed image. At the ending receiving end, we are receiving this compressed image, and by using this super resolution method, we are again getting a high resolution image. This is the example given here. So the super resolution was successfully used in the old film restoration and in remote sensing applications, medical imaging applications, like when we have low resolution MR image, and if we want to get a high resolution MR image, for that also we can use this super resolution. And in ultra HD and other fields also we can use this super resolution whenever we have the low resolution input and we are expecting the high resolution output from that input. In previous years, for getting a high resolution output from a low resolution input, we used some methods like interpolation based method and a reconstruction based method. In interpolation based method, we are taking the correlation between the adjacent pixels. For getting the correlation between the adjacent pixels, we are taking an interpolation kernel. So by using this interpolation kernel, we are calculating the correlation between the adjacent pixels. That's how we are trying to reconstruct the image. But this interpolation based method is having some problems like jagged artifacts and blurring issues and noise interference. So this is not being used in nowadays. And another method which was used in older days, reconstruction based super resolution. So this reconstruction based super resolution method is also, it is now not being used because they used a regularization term lambda, which is based on the edge smoothness and the global reconstruction constraint. But when we are reconstructing the images, the problem is some of the edges we are losing at that time. So this method is not suitable. Nowadays, we are using convolutional neural networks. Most of the papers which are addressing the super resolution, they are using the convolutional neural networks and the generative adversarial network for addressing the super resolution. So they are discussing in this paper, they are using a skip residual dense network as we mentioned, and they are also using a new joint loss function. By using these two, they are getting a very good high quality super resolution image, and they are also mentioning they are getting a very good PSNR and SSIM. Here in the related work, they are mentioning compared to the interpolation based methods like some bilinear and bicubic interpolation based approaches, CNN, the convolutional neural network based approach, is giving a very good performance for getting the high resolution image. So Dong, he is the person, he first proposed the convolutional neural network for the super resolution. When he applied the super resolution model for the convolutional neural network, he achieved a very good performance. After that, many papers from that onwards, many papers they are using this SRCNN. After the development of the SRCNN, many papers used this deep learning concept, means convolution networks for the restoration of the high resolution image. Some of them are the papers are given here: residual learning, Laplacian pyramid structure. There are some other. deep resolution convolutional neural network. It was proposed in this model. It is avoiding too many network parameters. That is the advantage. But at the same time, this proposed deep resolution convolutional neural network is taking the more convolutional layers for extracting the features. But the reconstruction is very excellent in this paper. In the that was given in the reference. Another method we have used VDSR. VDSR was proposed. The purpose of the VDSR is to get a very fast results and to achieve a very better results compared to the previous networks. So they are also taking a single low resolution image, and the target is to get a very high resolution image. The advantage of this VDSR method is we are getting the results very fastly compared to the existing methods. Later, they have proposed EDSR, enhanced deep residual network also. This enhanced deep residual network for the single image super resolution in this model, we are achieving a very good performance. How we are achieving the very good performance? We are removing the unnecessary BN layers from the residual black. After removing the unnecessary BN layers from the residual black, we are getting the chance for the expanding of the size of the model. Now, even though we have taken different models, we are using a matrix called PSNR performance. So this PSNR performance is good for all above mentioned models. What are the different models we have taken here? We have taken DRCN model, and we have taken VDSR model, and we have taken EDSR. All these proposed methods are giving example very good PSNR. Then we should not consider the model simply based on the PSNR performance, because there is a chance that whenever there is no information, when there is no required information from the image, at that time also we may get a very good PSNR values, which is giving output smooth results when we don't have enough details in the image. That's why so we are going for the another metric for the evolution. Why the problem with the PSNR is we are getting this problem is because PSNR measurement, it is fundamentally different from how we human beings evaluate a particular thing by using the human vision. Because of this difference only, perceptual driven methods we are proposing. So then there is another network which is SRDN. It is actually we can say it is a milestone in the pursuit of visual experience. In this SRDN, they are trying to improve the visual quality. For that improvement of the visual quality, they are combining the semantic image, and by using this semantic image means, if the example there is a blue color in the a pixel, if we get the blue color, now we are comparing this blue color with respect to sea, or with respect, we are comparing this blue color with respect to sky, and we are getting the details from the high resolution sky in order to restore this image. Example we are taking. Similarly, in this network, in order to restore the high resolution image, we are taking the semantic image. In this model, in this network, for that we are using a residual black and a perceptual loss optimization to when we are reconstructing this model. Even though we have used many methods previously, we have, as mentioned, they are giving good results, but they are having some shortcomings. Example, EDSR, whatever the method we have seen, and other some convolutional neural networks, other we have seen, they are not introducing the perceptual loss. When we do not use the perceptual loss, we cannot learn properly, and convincing results are not, we are not getting the convincing results. We are using some other networks like SRGAN and BEGAN. They are using the perceptual loss for getting a relatively good results compared to the EDSR, but their PSNR and SSM values are not good. Why this problem is occurring is there is a difficulty in the training. Even though we are trying to train it, we may not get the at what point we are getting the minimum loss, that convergence. Because of that, we are not getting that convergence. So there is a non-convergence problem. Because of these factors, in this paper, they are proposing a super resolution enhancement model method based on the skip residual dense net. So here they are combining the content loss, perception loss, and color discrimination loss, and they are constructing a loss function, which is the combination of this content loss and the perception loss and the color discrimination loss. They are using this loss function when we are training the network. So in the proposed method, they are taking SRDN network, which is proposed by them. First, the input image, they are dividing into two components. XB, one component they are calling as XB, and another component they are calling as XD. One is base layer image component, and second one is detail layer image component. Why they are calling with these names means this XB image component they will give to the base layer, and XD this image component they will give into detail layer. So they are giving these two components into two layers. That's why they are calling with these XB and XD. Now, how we are getting the XB and XD from that image? By using a guided filter. This guided filter is giving the two image components from the original image. What are these two image components? XB is the low frequency component from the image, whereas XD is the high frequency component from the image. What is this low frequency component? Whenever, example, we want to detect whether a cat is there in the image or not, at that time the cat face is high frequency component, and the background, whatever the background noise is there, that background, ground, everything, we can think this is a low frequency component. So when we want to get the detail layer, mathematically we are taking the original image X and we are dividing that with respect to the base layer XB. That division of X with XB is giving the detail layer, which is consisting the high frequency information. High frequency information means the edge details and the required information details are given to us. Now we are connecting the two filter components, whatever we got, XB and XD. We are connecting these XB and XD with the original image. And when we are connecting with the original image, we are getting the new components. Capital X base layer, which is representing, it has the information of original image and the information of the small xp, means the base layer image component, low frequency image component, background image information. And the capital X detail layer, it is having the information related to the original image and a detailed image information. Means detail layer information means the actual information, the edges we are looking for, the cat face we are looking for, like that. Now the output, this will be given to a convolution layer, and then from that we are extracting the features by using a 3-layer SRDN network. Each layer of the SRDN is consisting of 2 channels, and the extracted features from these 2 channels are combined by using the concatenation operation. After that, we are getting the final result through deconvolution network and convolution operation. Mathematically, this is how we are representing. When we want the XB, we are taking the guided filter, and that guided filter of the original image X is giving the base component, base layer component XB. And after we are getting the XB, we are dividing the original image with the XB in order to get the XD detail layer. This is how we are getting the XB from the guided filter. When we are applying the original image to that guided filter, it is giving XB. By using this XB, when we are dividing the original image with the XB, we are getting the XD, which is the high frequency component information. Whatever the conv we are seeing in the image, we have seen here the conv. This is representing a convolutional layer. This convolutional layer is having 64 filters with size 9 by 9. The filters we are taking, the kernels or filter, whatever we are taking, they are having the size 9 by 9. And we are taking the stride 1, and then we are applying the 2 X base layer and X detail layer information to the convolution layer, and then we are applying that to 3 SRDNs. After that, we are the features are extracted from the 2 channels of the SRDN, and we are concatenating, we are combining the features from the 2 channels, and then we are doing the upsampling. Here upsampling means we are doing the deconvolution, and we are doing the deconvolution operations, and then finally we are using a convolution layer. After that, we are getting a super resolution image. So we have given 2 input components. These 2 inputs components from the convolution layer are given to the SRDN. SRDN actually it is consisting of the 2 channels, as you have seen. The 2 channels, the upper channel is called as basic feature extraction network layer, and the lower channel is called as detailed feature extraction network layer. This is basic feature extraction layer because we are connecting the XB, capital XB, which is consisting the information of the image components of the basic layer, and this is XD, which is consisting of the information of the detail layer. Means XB is consisting the low frequency component information, background information. XD is consisting the high frequency component information, which is edges and everything. Now we are connecting that information to the channel 2. So that's why, so this is called basic feature extraction network, and this is called detailed feature extraction network. Even though the upper layer, which is a feature extraction layer, which is mainly designed for the reconstruction of the low frequency components from the color images, and the lower layer, which is designed lower network, which is designed for the extraction of the detailed feature extraction. So the upper layer is trying to extract the low frequency components, and lower layer, lower network is trying to extract the high frequency component. But some of the problem is some of the high frequency information may also remain in the upper layer. So in order to get that high frequency information, we are using a skip connection in this paper. That skip connection is from first upper network to the lower network. Means base feature extraction network to the detailed feature extraction network. The only purpose we are using this skip connection is in order to use that high frequency components, they are remaining in the upper network. So in SRDN network, in the upper basic feature extraction network, in the lower detailed feature extraction network, in both the networks, we are using 3 dB nets, where dB net means it is a dense block net. This dense block net, it is consisting of 3 layers. We can see that this is one dense block. Here we have considered 4 dense blocks. In this paper, they have considered 4 dense blocks. In the first dense block, we are having a BN layer. This is BN layer first, and the second layer is ReLU layer, rectified linear unit. We are applying the activation function rectified linear unit, and the third one is convolution layer. Similarly, again we are repeating another dense block, which is a BN layer, rectified linear unit, and a convolution layer. Like that, we have taken 4 dense blocks. And why the name dense block is coming means we are connecting this block with every other block. You can see the arrow from this block means we are connecting this block with this, and this block with other, and this block with another. So if we are connecting like this, then this connection is called as dense connection. That's why this block is called as dense block. We are using such 4 dense blocks in this paper. They are using 4 dense blocks in the DBNet. If we increment the dense blocks more, there is a possibility to improve the there is a possibility to improving of the results. We will get the better results. When there is a big difference between the statistical data of training and test set. If you are taking the training set example, if you are taking the training set, the number and the test set number, if there is a big difference, if you are taking 100 training samples, and if we are taking 2 test samples, and are we taking 40 training samples, are we taking some 200 testing samples. When there is a big difference in like that, generally we try to take much training data and less testing data. But if we are taking 100 input training data and we are giving only one or two testing samples, at that time there is a possibility that the BN layer, what we are taking, that BN layer is capable of adding the pseudo noise or bad pseudo influence, which will limit our prediction ability. So in order to, in this paper, they are mentioning to remove they will remove the BN layer. With this removing of BN layer, they will get a very good generalization ability. The computer memory also reduced. The memory usage, whatever the memory we are using, that the memory usage is also reduced computationally. It will become less complex, and also the performance will be increasing more. Now they are saying instead of ReLU, which is a rectified linear unit, they are replacing that ReLU with a PReLU, means a parametric rectified linear unit. They are taking this activation function in this new DB module. As we discussed previously, in this paper, they are taking the joint loss function, which is the combination of the content loss and the perception loss and the color discrimination loss for improvement of the super resolution quality. Now this is the content loss, which is a mean square error loss. The difference between the target and the original output, the predicted output, we are taking that difference square and we are performing the mean. Then that is called as mean square error. This is the content loss, and this is the perception loss we are taking, and this is the color discrimination loss. We are adding these three losses combinedly. We are calling this as a joint loss function. This is the mean square error. This is the ground truth. Ground truth means whatever the original high resolution image we are expecting, our image should reach there, that predicted value. If we are taking YT, which is nothing but this is the difference. This is giving the, as we mentioned, LMSE, it is giving the difference between the predicted and the original value. We are taking the mean square error. This mean square error is nothing but our content loss. It is giving the difference between our original high resolution image, which is GT. They are representing ground truth, which is our original image. Here YT is the predicted, whatever the image we generated by using our super resolution network, it is the predicted image. That correction you have to make. So ground truth is the original image, original HR image, and YT is what is the super resolution image that is generated by our network. Now we are taking the difference between them and we are calling that as a loss. That loss we are mentioning here. And then we are taking the perceptual loss. That perceptual loss, for that perceptual loss, we are taking LSR-VGG. This is a perception loss based on the rectified linear unit activation layer of the 19-layer VGG network. So we are taking the perception loss based on the rectified linear unit activation layer of 19-layer VGG network. For getting this perceptual loss, we are calculating the pixel distance. Where we are calculating the pixel distance? In the feature space of the 19-layer VGG network. After calculating the pixel distance in the feature space of the 19-layer VGG network, the perceptual loss is obtained. Similarly, LRGB we are taking, which is nothing but the color discrimination error. It takes a cosine distance as the color discrimination loss. It is whenever LRGB term we are indicating, it always takes the cosine distance. So in this paper, they have taken DIV2K dataset for the training. The dataset, the training samples they have taken from the DIV2K dataset. They are performing 1000 epochs. Initially, the alpha they have taken 0.1. And gradually they are decreasing after each epoch. The learning rate, they are decrementing alpha value, they are decrementing for each epoch. From first epoch to 1000 epoch, the alpha value in first epoch from 0.1, it is decreasing until the 1000 epoch. And the momentum they have taken 0.9. This is the momentum they have taken. And for optimization, for the minimizing the loss, joint loss function, they have used the gradient descent optimization method. This gradient descent optimization method is finding the minimum of the loss function. For what parameters we are getting the minimum of the loss function, which is using the Adam algorithm, and the batch size they have set into 8. At a time, they are giving the 8 training samples at a time. That's why the batch, we can call this as a mini batch. The hardware requirement, they are using Intel, and also the software they are using TensorFlow 2.0, 2.0 framework, and Python 3.7, and Linux. OS is Linux. So now we have taken a div2k dataset for the training. PSNR values are very important to us. So we are checking the PSNR values after the each epoch. From first epoch to the 1000 epoch, we are taking the PSNR value. You can observe in the diagram, the PSNR value at 0 is very minimum. So it is increasing with the number of epochs. Almost at 100 epochs, we are getting the higher value, and it is becoming stable from there. So we have considered 1000 epochs. So PSNR value is maximum at that 1000th epoch, which became stable from the 100th epoch. As we mentioned, after the 100th epoch, there is no much change. After the 1000 epoch, it is almost becoming stable. So in generally, for the amplification, or for the 2x super resolution, or for the 4x super resolution, so in this paper they are suggesting 1000 epochs will give the better PSNR value. So in order to check the superiority of the proposed algorithm, how much superior it is, they are taking 2 model parameters, means 2 HF files. These 2 HF files, which are containing the model parameters, they are obtained by 2x and 4x super resolution networks. So we are taking 2 H5 files. One is related to the 4x super resolution. Another one is related to the 2x super resolution. We are taking the 2 model parameters in the HF files format in order to check the superiority of our proposed algorithm. After training is completed, now they are using 2 data sets, set 5 and set 4, set 14 data sets. They are commonly used data sets in the super resolution. So they are taking the same set 5 and set 14 data sets, and they are testing this model by using these 2 data sets. So they are comparing the results with the bicubic method and SRCNN, super resolution using deep convolution networks, and EDSR, super resolution using very deep convolution networks, and SRGN, means super resolution using generative adversarial networks. They are comparing the results with these 4 networks. So in the images, we will compare the different models. For the 2x magnification factor of the super resolution result, for the input image, lower for LR input image, actually we are taking the test image, and we are downsampling it by 2 times. So twice downsampling is done, and after that we are using the super resolution twice for all networks in order to get the 2x magnification factor. Similarly, for the 4x magnification factor super resolution results, we are downsampling 4 times. The 4 times downsampling is done on a test image, and a quadruple downsampling, and a quadruple, after that quadruple super resolution is applied with the proposed algorithm in order to check whether how much super resolution is being given. So they have taken the super resolution original HR image, this one original image, and this is obtained by using the bicubic algorithm. This is the super resolution image which is obtained by SRCN algorithm, and this is obtained by VDSR algorithm. and this is obtained by SRDN algorithm, and this is their proposed algorithm output. Similarly, they have taken other image, the original, this is the original image, and with the different models, and the final one is the with the proposed, whatever the model they have proposed, with that the super resolution, how they are getting that images. Next, in the objective evolution, we are taking two parameters, PSNR, peak signal to noise ratio, and structural similarity index measurement. The PSNR value should be high. If the value is high, then we are having a very less noise. The larger the value of PSNR, the better the quality of the super resolution image. And the SSIM value should be close to 1. If the closer the value to 1, then we are reconstructing the original HR image, because it is structural similarity index measurement. So PSNR value should be high, and SSIM value should be near to 1. So we will check the different models. They have taken the two data sets, set 5, set 14, one for the 2x resolution and another for the 4x resolution. For the bicubic and SRCN and EDSR and SRJN, when they are comparing, the proposed model is giving the PSNR 33.5 and structural similarity index that is 0.95. Now they have mentioned for the 2x super resolution, 4x super resolution, we are getting the better results. Table 1 is giving the results for the 2x magnification, and table 2 is giving the results for the quadruple magnification. These two are two different data sets. So in conclusion, they have mentioned, they have used here a SRDN skip residual dense net, which they have proposed. It divided the input image into two components by using the guided filter. After that, they have given that to SRDN network. In that SRDN network, we have used 3 DN net blocks, dense net blocks. Each DN net block is consisting of 3 layers. One first layer is used for the BN layer removing, and second layer is used rectification linear unit. They are using PRELU. They have used here, and the third layer is convolution. Now they have extracted the features from the upper channel and lower channel, which is upper channel is the base feature extraction network, lower channel is the detailed feature extraction network. After that, they have combined these two features by using the concatenation, and then by using the deconvolution and convolution operations, they are getting the high resolution image. They are saying their results are very good compared to the other existing models, and the output image is very clear and natural for the human visual reads, and it is getting very good PSNR and SSIM values. You can get the references here.